that involve the collisions between two objects. For each one, we're going to draw a picture that represents the problem and then make a table to put all of our information about momentum and then use that to solve any missing information that we don't have. The first problem we're going to look at is an inelastic collision. That's when one object collides with another object and they stick together afterwards. A 1,000 kilogram train engine moves at 3 meters per second and collides with a 5,000 kilogram freight car initially at rest. Assuming no loss of momentum, what is their combined speed after the collision? First step for each of these is going to be to draw a picture. And the picture should summarize all of the information in the problem. You don't have to be a fantastic artist as long as all of the information is in the picture. So our first situation is a 1,000 kilogram cart moving at 3 meters per second and a 5,000 kilogram car that's initially at rest. So I'm just going to draw a 0 that represents at rest. After the collision, they move together. So there's my 1,000 connected to my 5,000. And I want to know how fast they're going afterwards. So that's a question mark for me. Okay. I'm going to put my table to use each time. You can call it start and end, or fancy words are initial and final momentums. And I'm going to make a line for the engine and a line for the car, and then a line for the total, or sometimes we use the word system momentum. So the engine at the beginning, and this is going to involve a little bit of calculation, the engine at the beginning has a momentum of 3,000 kilogram meters per second because it's 3 meters per second times 1,000 kilograms. So that formula for some side work, P equals mv, it's the only formula you're going to need. Little side work over here. All right, 3 meters per second times 1,000. That's my momentum of my engine. And then the car at the beginning is 0, and the total, therefore, is going to be 3,000. Which means we're going to assume momentum is conserved, that there's no loss of momentum outside the system, that afterwards, together, they had better have 3,000 kilogram meters per second of momentum. I'm going to change my table here a little bit because I know that afterwards they have a combined momentum because they have a combined mass, right? So together they have a combined momentum of 3,000 kilogram meters per second. To figure out their speed afterwards, I'm going to rearrange my momentum formula, solve for velocity. And so my speed, my velocity, is equal to momentum divided by mass. And in this case, my momentum is 3,000. And my combined mass, 5,000 plus 1,000 together, my combined mass is 6,000 kilogram meters per second. And so my speed afterwards is 0.5 meters per second. Right? So together, they're moving 0.5 meters per second. They must have the same speed because they're stuck together. An elastic collision is a little bit different, where objects collide with each other and then don't stay together. They have different velocities afterwards. So we have a little bit more information to deal with, but our process is still going to be the same. I'm going to draw my picture, make a table, and then solve the problem. There's an 8 kilogram ball that rolls down a track at 10 meters per second. So I'm going to call that 10 meters per second up here and draw an arrow. Collides with a 5 kilogram ball initially at rest. So I'll draw that 0 again, and then a little dotted line to let me know that that's the before. Afterwards, it says the 5 kilogram ball moves forward at 12.3 meters a second. So that's a little bit faster, 12.3 meters a second. And we're trying to figure out what happens to the 8 kilogram ball. So that's my question mark. Again, I'm going to set up my table with initial and final information. Initial and final. And I'm just going to indicate the differences between these with their masses because they're both the same type of object. All right. So we got a 5 kilogram and 8 kilogram, and again, the system or the total momentum. The 8 kilogram ball initially has 10 meters per second of velocity, and so its momentum initially is 80, and the 5 kilogram ball is at rest, so its initial momentum is 0. So the system had better have 80, which means at the end, the system should have 80 as well, assuming no loss of momentum. The 5 kilogram ball is now moving at 12.3 meters a second, so I need to do a little side work. 5 times 12.3 tells me that I have 61.5 kilogram meters per second of momentum for the ball, which means the 8 kilogram ball has to have the rest, right? Whatever's going to make the total 80 there. So I think that should be 18.5 kilogram meters per second. Now I can use that 18.5 to figure out the speed of the 8 kilogram ball. I know it's going to be positive. It's still moving forward because my momentum's positive, but to calculate the actual number, V equals momentum divided by mass, which is the same thing as 18.5 divided by the mass of 8. And I get about 2.3 meters per second. And just checking to see if that makes sense. Does it make sense that the larger object should still move forward but slow down quite a bit, and the smaller object moves forward but pretty quickly? I think that makes sense. The final scenario is an explosion, and it doesn't have to be something that actually lights on fire and explodes, but that's anytime there's two objects that start together and then split into separate pieces with different velocities. But we'll give you an actual explosion as an example. A 2 kilogram ball rests inside a 40 kilogram cannon. Both are initially at rest. When the cannon fires, the ball shoots out at 25 meters a second. What's the velocity of the cannon after it fires? So I'm going to start by drawing these two things together. Here's my 2 kilogram cannonball and my 40 kilogram cannon. And those are initially at rest. Actually, I'm going to change that. I'm going to put the cannon on the other side so that the ball shoots rightward. So there's my 40 kilogram cannon. So that's the before. And then afterward, the ball is going to move pretty quickly at 25 meters a second. And the cannon is our unknown, right? We don't know which way that's going to go. Or we know which way that's going to go. It's pretty clear that it's going to go backwards, but we're not sure how quickly, right? So let's see if we can figure it out by using the same table method. We've got initial and final. We've got a ball and a cannon. And we've got a system. And I know they're both at rest, right? They start together, which means our system momentum is 0 to start, which means afterwards our system momentum had better be 0. If I look at the ball's momentum, 2 kilograms times 25 meters per second, that's going to get me 50, which means the cannon must have negative 50 of momentum, negative 50 kilogram meters per second of momentum, because the total has to be 0. And same method as before. How do I figure out the speed afterwards? Speed is equal to momentum divided by mass, which in this case is negative 50 over a mass of 40, and we're going to get a velocity of negative 1.25 kilogram, sorry, not kilogram meters per second, just meters per second after the collision, right? After the explosion, because we know that it's got to move backwards if the ball moves forward and they're initially at rest. Thanks for watching. Check in with your teacher if you have any questions.